Everyone, welcome back to Physical Geology 1403. How we doing? Yeah? Ready for week 2. I love that attitude. Keep it up. Let's see if you have the same attitude on week 7. All right. So, how was our weekend? What did we do? Anyone do anything fun?
Nothing much, honestly.
Nothing?
Nothing of note.
You had a what? You had a gig? A gig? Oh, you played with your band. Awesome. Very cool. Very cool. Are you guys good? If you get paid to go and play? Yeah. Of course, you're a little biased, but yeah. I don't know. All right. Anyone else? Anything you want to share? No? All right. Cool. Last time we talked about matter and minerals. What questions have y'all thought about that? What questions have you come up with as you've been reviewing and writing your notes and submitting your notes? How do we feel about matter and minerals?
Very minerally.
Very minerally?
Why are minerals like equally different as they are the same?
Why are they equally different as they are the same? You could give a philosophy professor nightmares, my friend. I'm not sure what you mean by that. Can you say it in a different way?
I don't know. Just as doing the assignments and reading over the notes, it feels like a lot of the minerals that, well, I guess the ones that we're looking at,
Okay.
have like distinctive features, but also sort of features in a way it's like you can tell one apart, but you gotta really pay attention.
I'm actually going to put this microphone over here, and hopefully that'll catch some of the audio from what y'all say back here. All right. Your question is, why do minerals, let me see if I can summarize it. Why do minerals share a lot of the same characteristics, but then not others?
Yes, but I feel like that they have this like their own unique features. I guess it just kind of depends on conditions of each individual mineral. But
Yes.
Like I said, doing the assignments, I feel like a lot of them have like if I were to not really pay that much attention to from one mineral to another, I wouldn't be able to tell the difference. But they do have distinctive features.
It's those little differences that make them separate minerals, individual minerals that we classify differently. Think of it like this. Our friends over here are sorting M&Ms, right? How are they sorting them?
By color.
By color, okay? Besides their color, are those M&Ms the same in every way? Yes, they are, until you look at each one individually. Some of them may have the left part of the M scratched off. Some of them may have the right part of the M scratched off. I could separate them further by the ones that have the left part of the M scratched off versus the ones that have the right part of the M scratched off. Some of them may be broken in half. Okay? Maybe they're broken in half crosswise to the M. Maybe they're broken in half parallel to the M. Right? I could separate them by that. These M&Ms, there are enough of them that they have some things in common. I would probably have a population of blue M&Ms that are broken one way versus the other and have the right M scratched off by the time I'm done with this. It is their individual properties that make them distinct, though they may all be grouped under the same classification of M&Ms or minerals, if you're catching my drift here, right?
I guess it could kind of be like the same way as flora and fauna. They all have like similarities, but also distinct characteristics.
Think of it as the taxonomy, right? Here we live on an earth that is full of life. We just classify it all as one broad category, life. But then we break it down into things like prokaryote and eukaryotes, right? And then we break those down even further into bacteria, archaea, so on and so forth, until you end up with the distinction between bats, whales, humans, dogs, and cats. And then even further in the human race, if you wanted to go there, people who have genetics that prove that they were, say, that their population came from maybe northern Europe, like mine did, versus someone whose population came from Southeast Asia, someone whose population came from South Africa, so on and so forth. We are all part of the same species, but we classify based on a few distinct characteristics inside our DNA, some of which are manifest on the surface. Perhaps eye shape, perhaps skin color, perhaps compressed hailstone, right? Different classifications based on different properties shared among individuals. Does that make sense?
But minerals aren't people too.
Minerals are not people too.
Not people too.
They are not. No, but the logic follows, if you understand what I'm saying.
Definitely.
It is those unique properties that minerals that formed in the same situations have in common. That's why we classify them as the same thing, right? So all over the world, no matter what, I am probably going to find olivine formed at around the same temperature and pressure regimes. No matter where on Earth it's found, the same conditions probably existed there when those were formed. All right. Good question. Anything else?
If like minerals are made with like other minerals, wouldn't they be rocks?
Yes. Okay. So the question was, if minerals are made with other minerals, wouldn't there be a rock? And the answer to that is yes. Do I have? I don't have it on me. I'll just grab one of these. Here I have a rock that we are going to become very familiar with this week. Okay. This is a rock. It's actually a slab of countertop carved from a rock. So I'm using it because it's got this nice flat polished surface, so you can see what I'm talking about here. This is a rock, but do you see all the minerals in it?
Yes.
You see that there's a lot of minerals in it, right? Why am I calling each one of those a mineral? Remember our definition of a mineral?
Crystallized.
Right, there's a whole bunch of stuff has to be naturally occurring inorganic solid with a crystalline structure and a chemical formula, right? But what you're seeing are copies of minerals in there, right? These kind of pinkish white ones, that's all the same mineral, but different crystals of them. If this were all that mineral, I would just say it's the mineral feldspar. This is a huge chunk of that mineral right there. They're not exactly the same size, but you get what I'm going for. If it was all one mineral, I wouldn't necessarily call this a rock. I would call this a mineral. This rock is made out of a whole bunch of minerals. What else do we have in there? Well, there's those clearish, almost transparent gray ones, okay? That's the second mineral. Now that I have two minerals in this substance, I call this a rock. It is no longer a mineral. It has become a rock because it is a mix of multiple minerals. Please don't eat your M&Ms until we're done with the exercise like later in the lecture. Okay? Wow. Then we've got these black minerals and so on and so forth. Because this is a whole bunch of minerals all combined together, it's a rock. So yes, when multiple minerals form from the same magma, you form a rock.
But this was here a mineral, right? But like I have different colors.
Right. So how many minerals do you have?
Like three.
Well, there's two. There's two minerals in that. That comes from your lab, right? That's on the lab, right? It's the green minerals that you're looking at in particular in that sample. The green ones are the ones that matter there.
There's two minerals in here.
Good question. Any other questions before we get started? Everyone have their M&Ms?
Do you want yours?
You get some too. Thank you. I don't get one. It's very nice. Thank you for making one for me. All right. Everyone has M&Ms?
Yes,
All
sir.
right, good. Hold on to that for the next hour and a half.
Yay.
Yes. This is a practice in self-restraint. Okay. That's not the main reason, but it's a good exercise.
Fun.
All right. Any other questions? I want to make sure that you all feel comfortable with what we've already discussed before we move on.
None for me.
And for those of you watching this online later and feel left out because they don't have M&Ms, I'm not stopping you from getting M&Ms. Stop the lecture and go buy yourself some M&Ms. You will see on the screen the exercise that they will be doing with the M&Ms here. And you can follow along if you so desire. Okay. Shall we begin? Okay. Today we are talking about igneous rocks and intrusive activity. Just for now, I'm going to mute that.
Oh, it's the
That's
drone.
not mud at all. What do you mean?
What am I looking at in that picture or in these videos?
Volcanic
Okay,
activity.
volcanoes. And what is it spitting out? Lava. Good. What is lava?
Melted rock.
Melted rocks. Okay. I feel like you all are pretty certain you know what's involved here. Today you're going to learn a lot more, believe me. Okay? What we are looking at here, why is it hot in the first place? Why is it melting? Why is it bubbling? Why is it exploding? These are things that we are discussing this week. Today, in particular, in this lecture, we are learning about what goes on underground to make this in the first place. And then on our next lecture, we are going to learn about what makes them go boom. Okay, we're going to talk about that a little bit here today, but that's mostly going to be what we're talking about in our next lecture, what makes them go boom. Okay, have you ever heard the term magma?
Mm-hmm.
Yeah? In what context? What is magma?
Well, in context of lava.
Don't read. Okay, yes, what is magma?
Like cold lava.
Rock near the core.
Lava near the core? But
Closer to the center. It's pressure.
is there lava down there? What did we learn about last week? How many liquid layers are there in the earth?
One end of the
Just one. The outer core is the only liquid layer in our earth. So that's just melted metal, by the way. It's just an iron nickel alloy with a whole bunch of other dense metals in there, as far as we know. Okay? So I don't know that I would necessarily refer to that as magma per se. And that never really comes to the surface anyway. That's way too deep. Okay, so where is this coming from? This is melted rock. This ain't core stuff. What is magma? I'm going to ask that again. Let's get one more answer.
Solid rock.
It's not solid. It's this liquid.
That's some solid.
All right, here we go. Magma and lava are the same thing.
Wow.
What? Yes, revelation.
I said that.
Mind blown. Wow. You guys seen that meme?
Yeah.
Wow, that's so funny.
Kabloom.
Okay. Here's the difference. We call it lava if it's on the surface. We call it magma if it's underground.
Ooh, I like that.
Yeah, that's the right terminology. So, henceforth, if you say all this lava underground, I'm going to go,
Boink.
I'm not actually going to slap your wrist. Don't worry about it, okay? You can't touch you. Otherwise, I'd be going with marshmallows and fall asleep in my class. Okay? Magma is underground. Lava at the surface. We clear on that?
Yes, sir.
Cool. All right. So, what do we got here? The mantle is extremely hot, right? It's very hot. It's deep underground. It is absorbing all that heat that's emanating from the core. That heat on its way out to the surface, radiating from our core, goes through the mantle. The mantle is hot enough to be melted. Why isn't it? Do you remember?
Pressure.
The pressure does not let it melt. It is under too much pressure. If we reduce the pressure, it would probably melt. It would definitely melt. Okay? But how do you reduce the pressure? Exactly. You don't. And so instead, our rock gets slushy, squishy, still solid like Play-Doh, but malleable. And so the pressures that are constantly at play down there, moving and shifting as everything inside our planet is kind of moving around for one reason or another, it causes this hot mantle material to rise. This is called convection. Hot stuff rises. You're all familiar with that, right? Hot air rises. That's why it's nice to live on the second story of an apartment building in the winter, right? Because your neighbors downstairs are basically paying your heat bill for you, right? Okay. You live on the first floor, sucks to you, right? You're paying for your heat and your neighbor's heat upstairs. So, heat rises, hot water rises. How many of you have ever boiled oatmeal in a pot? What do you see? What's happening to your oatmeal? You see the circulation? Yeah, on the outside of the pot where it gets pushed up, the oatmeal gets pushed up, and then it gets pushed to the center where it kind of falls back down into the mix, and it does that. That's convection. Okay? So hot mantle material rises, bringing that heat with it. And as it approaches the surface, there will be a few things that can happen to it that could eventually cause it to enter a melted state. We'll talk about that later. I'm not going to spoil it for now, because that's a fun conversation. Okay? Okay, now, our magma and our lava have obviously a liquid component, but they also have a solid component and a gas component. Why do you suppose magma and lava could have a solid component? Why would some of it be in a solid state?
If this is like Play-Doh, it's like a liquid solid.
Well, I'm not talking about mantle anymore. I'm talking about magma. It
Oh.
has entered that melted state. For one reason or another, which we'll talk about later, some of it has melted. But why not all of it? Why are there some solid pieces in there?
We have minerals that don't melt.
Why don't those minerals melt?
They're too strong.
They're not too
They
strong.
have a higher melting point.
Ah, look at this! We figured it out! Okay, there are some minerals that have a higher melting point than others. Think about what you've learned so far. There are minerals that are harder. There are minerals that have different cleavage, minerals with different crystal forms. All these minerals have all these different properties. It shouldn't be that hard of a reach mentally to think minerals also have different melting points, right? So what happens if I take my rock and I heat it up to 1100 degrees Celsius? Everything's gonna melt except for that one mineral that only melts at 1200 degrees Celsius, right? It's called partial melting. We will talk about that more again later too. But that is why we often will have some solid components in our magmas and lavas.
Doink.
Okay? And why the gas? Well, gas is basically everything that was released from that chemical bond when it went from one state to another. Okay? So gases will often form as a result of going from solid to liquid, and then again from liquid to solid, because not all of the chemicals, not all of the elements there in that mix need to be in the new structure. Okay? So we'll often see things like carbon dioxide and sulfur dioxide and water vapor form as a result of going from one phase to another in magma or lava. Again, that will come into play later, because that's just my Okay. Here's an example we may all be familiar with when it comes to convection. How many of you have ever seen one of these before? What do we call these?
Lava
A
lamp.
lava lamp. There's a reason. Okay? Really, technically, we should call it a magma lamp, but the people who don't take my class or other geology classes may not ever know why. But now you can tell them. Okay? This is essentially what happens. What do we have here? We have a heat plate. Think of that as our core. Okay? Think of this as the mantle. We have this fluid surrounding another fluid that, upon the application of heat, loses density. How could we possibly lose density? How do you force something to lose density? When density lowers, what must happen? Well, it happens when you heat up things, but what exactly is happening?
It's more solid and like goes to the bottom.
It's not that it becomes more solid.
It's heavier.
Think of this as already a solid. It doesn't change. It is remaining a solid. It doesn't get heavier. Remember, we are reducing density. What is density?
How compact the thing is.
It is a mass per unit volume. What are we changing?
The mass
Are we changing the mass? How can heat change the amount of mass that something has?
release gas.
I mean, yeah, but at that point you're melting it.
Change the unit.
What unit? We've already agreed it can't change mass, so
State of
we must
matter?
change the volume. As you heat something up, it increases in volume. Okay? As it does so, the ratio between mass and volume changes such that your density drops. It becomes buoyant, or more buoyant than it was before. And so, as this lava lamp, let me play that again. As this lava lamp is going on, it is heating things up down here, and as it heats that stuff up down there, watch what happens. It's going to heat up, and then it's slowly going to start to rise off of that bottom heat plate. Why? Because that heat plate increased the volume of the space that it occupies, decreasing the density, and it rises. That's how convection works. Okay? Remember that. So, when our magma turns into rock, we are essentially going from a state of liquid to a state of solid. That's what's happening here. Yeah, yes, gases are released. But let's focus on the main event. Okay? Let's talk about this from the opposite way first. Solid to liquid. Let's talk about that. Atoms contain a lot of energy, right? They are all constantly vibrating. Okay? The more energy you put into a thing that contains atoms, the faster those atoms will vibrate. So you turn into a necktie. Okay? The faster those things will vibrate, those atoms. The more that they vibrate, the harder it is for them to maintain their bonds. Bonds are only so strong. They can only absorb so much of the vibration before it finally just breaks. The bond is released. It disassociates. And then we go from our solid state of a nice fixed framework of bonded atoms to a whole bunch of atoms that are loosely bonded with each other. They'll go over here, they'll bond over there. You have loose molecules. You don't have your distinct framework anymore. You have gone from your crystalline solid to a liquid. What happens if we keep adding energy? Those bonds are going to get even more unstable. Wherever bonds did form, they're going to shake and they're going to break apart, and then all of a sudden you're going to have a bunch of atoms that don't want anything to do with each other. What do we call that? Well, it could form an explosion caused by gas. Think about water. What happens? You've got solid state water. We call that ice, right? It's when there isn't that much heat. You add some heat, what happens? It becomes, it melts and becomes water. Why? Because the bonds holding your ice molecules together no longer can sustain that state. There's too much energy in the system, and so they disassociate from each other, and you have a whole bunch of H2Os that are no longer in a crystalline formation. They're in a loosely bonded liquid formation. Okay? And then you increase the heat even more, what do you get? Steam. Gas. H2O still, but what's happening? These H2Os are so energized they can't stand being around each other, so they disperse into the atmosphere. Okay? Think of it like that. Does that make sense?
Mhm.
Excellent. Okay. Now rock does the same thing. Okay? You remember those silicon tetrahedrons that we talked about last time? Silicon tetrahedrons, where are they? A silicon tetrahedron is made out of what?
Silicon.
One silicon and
Tetrahedron.
a tetrahedron formed by
Hydrogen.
not hydrogen.
Helium.
Carbon. Four. One silicon and four other things. What are they?
Electron.
Huh? Not carbon. Sodium. What are the two most common elements in the Earth's crust?
Nitrogen.
No, that's the atmosphere. We're talking about the crust. One was silicon, and the other one was? No, that's the most common mineral. Feldspar is the most common mineral. I'm asking about the most common element. 27.7% of the Earth's crust, I believe, is made out of this thing.
Carbon.
Carbon's actually fairly rare here.
Wow.
Of elements, I mean, we have a lot of it here, but it's by no means. I think it's like the 15th most common element in the Earth or something like that. Thank you. I appreciate that you all are looking through your notes. Yes.
Oxygen.
Oxygen. Okay. 4 oxygens, 1 hydrogen, make a silicon tetrahedron. Okay? Remember, those are the first bonds that form when your magma cools off to the point that bonds will in fact form. Okay? That's when you start to form those silicate minerals. The first silicate minerals that form have more space to grow, so they tend to make larger crystals. And this is where we start to talk about the characteristics that allow us to tell igneous rocks apart based upon their crystals. Okay? You want to get on there, buddy? Okay. Okay, let's start talking about how we differentiate igneous rocks from each other. The first thing is a description of its cooling environment. Let's call it that. Now, I need to put a huge warning out there. I'm talking to all of you in here. Pay attention. And I'm talking to all of you watching later. Okay? These words I'm about to tell you are not describing anything other than the cooling environment. These are not types of rocks. These are descriptions of rocks. Okay? Every semester, I always get a few students who use these words as rock names. I make it so obvious. All right, so don't be those people. All right? Intrusive igneous rocks form where, do you think? What does that word imply? Intrusive. Do you think that they form above ground or below ground? Below ground. Think of it as intrusive, in the earth, okay? They form in the earth. They are characterized by having larger crystal sizes. Based upon what we just learned about, why would intrusive igneous rocks have larger crystal sizes? This is what I like to call a logic train. I taught you, we just discussed, spent some time discussing a few basic principles. Now we're going to connect those principles together to form a conclusion to my question. Why would intrusive igneous rocks have larger crystal sizes?
Because when things like clump together due to their mass.
Clump together due to their mass. They are definitely clumping together, but that has less to do with their mass and more to do with the fact that it is now a solid versus a liquid. It has no choice but for all those minerals to be together, right? I'm asking about the size of the crystals. You had a comment?
I was going to say that they are closer together.
Okay, they do. That is true.
Is it because of their density?
Not because of their density. I love that you're throwing these ideas out. Keep them coming.
The cycle,
What cycle in particular?
the rock cycle.
The rock cycle. This is part of the rock cycle, but you're kind of using a macro scale view of everything to try and answer my tiny little micro question, you know?
Can you say the question again?
Yes. Why would intrusive igneous rocks have larger crystal sizes? Go.
They have more space.
Bingo! There it is! Thank you, Kate. All right. They had one more space. More space to what? Grow. Intrusive igneous rocks have larger crystal sizes because they had more space to grow. Why would they have more space to grow? How quickly do you think that magma cools down underground? Is it quick though?
No, years.
How quickly does something cool down in your oven?
Not that quick.
Not that quick. What happens if you take it out of your oven? It cools down quick, right? It had more time to cool down in your oven. It has more time to cool down underground. Ground is super insulated. It's hot down there. And while your magma may be hotter than the rock around it, that rock is still super insulating. It's absorbing that heat, but it's not disturbing it. It's not, it's not dispersing it as quickly as it would if it were on the surface, right? And so that heat cools very slowly. And as it's cooling slowly, your minerals that form first have more time to grow, and therefore you get larger crystals from intrusive igneous rocks. Now let's talk about extrusive igneous rocks. While we're talking about that, let me hand you this that I showed you earlier. Can anyone want to take a stab at what this is?
Marble.
Not marble.
Granite.
It's granite. Okay, this is granite. We will talk a lot about granite today. Notice how large those crystals are in there. How big are they? This is pretty big. You can see them easily. Intrusive igneous rock. Now, extrusive. Where do extrusive igneous rocks form?
Outside.
Outside what?
The volcano.
On the surface. On or very close to the surface. Now, will those form large crystals or small crystals, do you think? Small. Why?
They cool down real fast.
They cool down too fast. There's no time for them to make great big crystals. Okay? You follow me? Here's an example of an extrusive igneous rock, one that cooled very quickly. Okay? This particular one is called basalt. B-A-S-A-L-T. Basalt. Okay? You can look as much as you want. Some of you with extremely sharp eyes, good vision. Who has perfect vision here? I am very far from perfect vision.
Oh my God.
I mean, 2020.
Yeah, I have terrible vision. Like, I'm at the point where I almost can't wear contacts. My vision is so bad. Yeah. My wife, on the other hand, has 20/15 vision. She has better than perfect vision. She likes to make sure I remember that fact very often. So she might be able to see a few of the larger crystals in there, but for the vast majority of us, you'll need a microscope to see any of those crystals. Why? It is extrusive. It formed at the surface. Okay. Again, that tells you nothing about its composition. That tells you nothing about anything except the environment that it cooled off in, that it formed in. That's the only use for the words intrusive and extrusive. Do not use those words to describe composition or rock names or anything like that. You understand? Great. Now let's start talking about composition. Okay? By composition, what do I mean? What does composition mean?
What is composed like made of?
What it's made out of. Exactly. Thank you. Think of it like a cookie, right? That cookie that I talked to you about earlier. If a cookie is a rock, each ingredient is a mineral. Each rock has its own particular composition of elements. Okay? And those elements make minerals. Let's talk about this. That granite that I just passed around to you, I think it's still making its way around. Is it over here? It's right here. Oh, it's right here? Perfect. Let me have that again. Thank you. Okay, this granite, would you say it is lighter or darker in color? Lighter, okay. Those gray minerals that you see in there, those are actually white to transparent, but they just look darker because they're against the background of the white and pink minerals, okay? So if you count the grays and the whites and the pinks as light colored minerals, would you say that this is lighter or darker in color for sure? Lighter for sure. This is made out of mostly light silicate minerals, okay? An igneous rock that is formed from mostly light silicate minerals has a composition that we call felsic. Felsic. If you want to think of it in terms of how you break that word down to try and remember, think fel for feldspar, the most common light silicate, right? And sic is a suffix. Think of that as meaning silica, high in silica, okay? Here is a good rule of thumb when it comes to silicate minerals. We'll talk more about this a little later, but this is still relevant. It harkens back to what we learned last week. There is an inverse relationship between the amount of silica that a rock has and the amount of iron and magnesium that rock has. So when I am high in silica content, I'm low in iron and magnesium content. And the opposite is true. Now when I say high to low in silica content, obviously these are all silicates. There's still a substantial amount of silica in there. But when I say high in silicon content, I'm talking about like 40%. When I say low, I'm talking about like 27%. Okay? There's still a lot in there. It's just low comparatively speaking, okay? Nevertheless, this inverse relationship is true. High in silica content usually means lots of light silicates, very few dark silicates with iron and magnesium content. When you have a rock that has lots of dark silicates and it has a darker color, you have lots of iron and magnesium silicates and very few light silicates, which will have those extra silicons that come with it. Okay? Just remember that. Okay?
So felsic is high in silica.
Felsic is high in silicon content because it is high in those light silicate minerals.
And mafic is low on silica because it's high on iron.
Yeah, you're jumping ahead here. Mafic is on the other end of that spectrum. Mafic is like that basalt that I passed around, which we have right here. Would you say it is generally darker or lighter in color?
Darker.
Darker. This has a high percentage of dark silicate minerals in it. Sure, microscopic, but still you can obviously tell that that is the case, right? You don't necessarily need to see them. The general color of your rock can tell you whether it's rich in dark silicates or light silicates. There are definitely some light silicates still in here, but the majority of this is dark silicate. This is mafic composition. Let's break that word down. Think of it as Ma for magnesium. I know it's manganese, but think of it like that. It's Ma magnesium. Okay. Fic for iron. Good. Okay. All right. Quartz is made out of what? Who's going to remind you what quartz is made out of?
Silicon.
Always see silicon.
Silicons, perfect. SiO2, literally just one silicon, two oxygens, that's quartz. Quartz is a light silicate. That's a big reason why our felsic rocks, felsic compositions, have a much higher silica content. It's because of the presence of quartz. That's a huge reason why. All right. Okay. Now, what do you suppose intermediate means?
Between.
Where would it land on that scale?
Between.
Yeah, between felsic and mafic. Bingo. Intermediate compositions land between those two. So when I say between, I don't mean it always has to be like 50%. It's not going to be 50-50. Okay. Well, I mean it can be, but it doesn't have to be. Okay. There's kind of well, make up your mind, buddy. How do you want to go? There we go. Okay. There's kind of a scale here. Generally speaking, if there are 25% to maybe 60% dark silicates present, we're going to start calling it an intermediate. More than 25%, and there's so many dark silicates in here, I can't really call it a felsic rock anymore. Okay? And so that gets us intermediate. Would you say that there is definitely more dark silicates in this rock than there were in that felsic? Can you still see visible light silicates in here, and therefore we can't really call it a mafic? Perfect. This is an intermediate rock. Okay. This is called diorite.
It's beautiful.
Isn't it?
Not in Minecraft.
So many Minecraft comments in my classes. I can't begin to understand why.
But they have granite and things of such, so even that boards.
Okay. Now, on the way far side over here on this spectrum, behind mafic, way further back than mafic, we have something called ultra mafic. It is a super mafic, right? What could ultra mafic mean? If mafic rocks still have the presence of some light silicates, what would ultra mafic be? This is rock that forms so deep underground that really you only have the dark silicates. This peridotite is ultramafic. The greens, olivine, dark silicate. The blacks, pyroxene, dark silicate. There's nothing else in there. This is an ultramafic rock. Far rarer to find these at the surface because they come from so deep in the mantle. Any questions about that? Okay. Remember, all your rocks are going to fluctuate with the amount of silica that they have. Typically between 40 to 70% on the high end, 40 to low 30s, high 20% on the very, very, very low end. Okay? But they're mostly going to land between that, okay, between the 40 and 70. And you've got that inverse relationship. Okay. Now, what exactly? Let me pose that a different way. Silica content has a few influences on the behavior of lavas and magmas. Namely, it has to do with the viscosity. What is viscosity?
The way it flows, the way that it moves.
The way that it moves. Okay. Anyone want to add to that? Can anyone give a better explanation?
The resistance to flow.
Thickness. Okay, so that's a word that people will often associate with viscosity. The thickness of something. What did you say?
The resistance to flow.
Oh, now he read the slide. Okay. Viscosity is resistance to flow. How viscous is water? Does it flow easily?
Yes.
I'd say so, right? Matter of fact, we generally compare everything else to water as far as how viscous it is. Water is kind of our baseline. Some things flow easier. Some things do not.
Give it a bit.
Oh,
Just wait.
there it goes. Hey, look at that. Blech. Gross. What is this, by the way? Do you know?
Honey.
No.
Water, oil, grease.
No, that's corn syrup, my friends. This is in all the candy you eat. If you like gummy bears, if you like fruit snacks, this is what you're eating.
Yay.
Yeah. Cheap to make, comes from corn. Very sweet. Your body can't process it very easily. That's why there's this huge obesity problem. It's because mostly from this. Your body can't process it, and it's the cheapest sweetener out there. So, this isn't a diet class. I'm not going to go there. But smart choices, my friends. Smart choices. All right. Now, highly viscous or not viscous?
It's very viscous.
Very viscous. Remember, low viscosity means high flow. Low viscosity means high flow. That's what I said. High viscosity means low flow. When I say something is very viscous, that means that it flows very slow. Okay? Now, what does that have to do with silica content? Remember, what are our silica tetrahedrons doing early on? They're the first things that form. The more of them that form, the more bound up our liquid becomes. Okay? It's cooling. Silicon tetrahedrons are forming. Bonds are forming. It can't flow as easily with all those bonds happening, right? So our magmas with a composition higher in silica, therefore, more silica tetrahedrons are forming, are going to be more viscous or less viscous?
More.
More viscous. Bingo. Okay, here we have a flow from a mafic magma. It's flowing pretty well, right? It's going pretty fast. Matter of fact, some of these can flow at about 35 miles an hour.
Oh.
The hotter, faster ones. It's faster than you can run, so I hope you at least got a bike, right? Okay, this is from a felsic flow. You can barely even tell it's moving. It's going so slow because it has all those bonds that are forming, binding it up. That's corn syrup. Okay? Let me turn the temperature back up here for this next part. Not the temperature. Let's turn up the heat. No, I'm turning up the volume. Okay. Wait for that to disappear. I want you to listen during this video clip. Tell me what you hear. You're going to hear the sound of the wind in the camera. Apologize for that. Ignore that. Listen behind the sound of the wind. Okay? Lego pieces? What was that?
Like some of glass.
Glass doing what?
Shattered.
Breaking. Why would this sound like glass breaking? By the way, so much louder in person. It sounds like 1,000 dinner plates being shattered all at once constantly. What is happening to make that sound?
Cooling down.
Breaking down.
The lava is heating up the cold rocks in the rock.
Okay, so your hypothesis is that this lava is heating up the cold rocks under it and it's cracking that rock. Interesting thought. That isn't what's happening, but I like the thought.
cooling down.
What's cooling down?
The lava
The lava is cooling down where?
on top of more lava.
On the
The top
surface.
Exactly. The outer surface is cooling off. How fast? Very fast. What's at the surface that could suck away that temperature?
Rock.
Name all the things that could take it away. The rocks underneath of it could be stealing that temperature. The air, the atmosphere is a huge one. What else? What happened? Who says that this necessarily has to be above water? Matter of fact, there's more lava expressed under the ocean than there is on the surface of our
Like
continents.
thermal vents.
Yeah. Okay, so you've got lots of things on the surface. You've got water, you've got air, you've got the rocks around it. Okay, all these things are stealing that temperature away super fast. What happens if I remove the temperature from a flow of lava very quickly? The outer surface instantly cools and it becomes something.
Breaks down.
Obsidian.
Syrian.
Volcanic glass, obsidian.
Wow.
And that's what you're hearing. As it's cooling off and becoming that thin layer of obsidian on top of the flow is still pushing behind it, and it will crack and break that obsidian and push it further. And then as something pushes out, it will cool off, and then it'll be cracked and broken as more lava is pushing behind it. And so you get this formation and breaking, formation, breaking, formation and breaking on this volcanic glass constantly along the entire surface of this flow, and it's ear splitting when you're actually that close. Okay.
You took the video?
I didn't take this video, but I've been this close to a lot of lava flows. This is the best video I could find of this. My videos that I took either didn't have better sound quality or weren't able to show it with this quality. It's hard to get good sound on a video out in the wild. The video is usually beautiful, but the sound can be really tough to get down. Yeah. Yeah, you can also. Any other questions before we keep moving? He just ate on Saturday, so it'll probably be kind of slow. I have a video of him eating. I can show you all later if you want.
No,
Sure. Wait, did I get that on video? No, I don't think I did. I don't think I got that on video. I have one from a few months ago that I can show you. Okay. We good? All right. So let's talk about igneous textures. Texture is the first kind of key word that you need to know for identifying igneous rocks. So far, we've talked about cooling environment. We've talked about what happens as it's cooling down and all of that. Now let's talk about what is you actually need to know as far as identifying these rocks, telling them apart from each other. This will be useful for the lab. Matter of fact, these are the exact things that you need to know for the lab. What can affect the texture? First of all, your texture is the size, shape, and arrangement of the crystals in your igneous rock. What can affect these things? Well, how did it cool? Quickly, slowly. We know that affects the size, right? What is it made out of? That will determine the shape that you can form as well, okay? So name how much silica there is. Is it a light silicate, a dark silicate? Okay. How quickly did it, how viscous was it, I should say, okay? While it was moving, while it was forming, okay? How much gas is there as well? The amount of dissolved gases that are trapped in your rock can determine some things about it. Specifically, does it have any holes in it? You may have noticed when I passed around that basalt earlier, there were a few little holes in that rock. What formed those? Gas. We'll talk more about that in a minute. And then, of course, if it was cooled extremely quickly, we get volcanic glass. We call that quenching. If it's instantly quenched, this usually happens in the presence of water. Okay? If it was instantly quenched, you make that volcanic glass. Why does it make glass instead of minerals in a rock?
Because it's extremely heat.
There was no time to make that. What did form? Silicon tetrahedrons. They were the first things that formed. But then if you instantly, or almost instantly, suck away all that heat before any minerals can form, you're left with just the silicon tetrahedrons. It's glass. Okay? And it's usually colored. It's usually these blacks, these reds. There's also some very vibrant greens like this. Okay? What colors it? Whatever was in that magma that didn't make it into a mineral because it was cooled too quickly. Black, red, green, rainbow, white in some cases. Okay? Just depends on what else was in that magma or lava. lava that's making obsidian, right? So our first igneous texture is going to be aphanitic. Yes, this is very relevant to lab, so please take good notes. Aphanitic textures are fine grained, which means intrusive or extrusive. Bless you.
Bless you.
So what?
Aphanitic textures are fine grained, very tiny crystals, microscopic most of the time. So was this rock formed intrusively or extrusively?
Extrusively.
Extrusively. Good. Small crystals, shorter cooling span on the surface or near the surface. Aphanitic texture is going to be what that is. That's like the basalts I passed around. Okay? Very fine grained. You usually can't see them without a microscope. Oftentimes, we will also see these things filled with holes. These holes are called vesicles. V-E-S-I-C, and then vesicles, L-E-S, or vesicular is the description of it, U-L-A-R, right there. Vesicular. So if I were looking at an igneous rock, and I could see that all of its minerals were microscopic, I can't see any of them, I would describe it as aphanitic. But then I also see that it has holes in it. I would say it is vesicular. This is an aphanitic vesicular rock. Both are true. Okay? Now, why do those vesicles form? As our rock is cooling, and we know that it cools quickly because it's at the surface, it's aphanitic, right? As it's cooling, those gases are forming as it's going from a liquid to a solid. Okay? Those extra unneeded elements, those volatiles in there that can't get incorporated into the solid out of the liquid, they're going to form pockets of gas. What does gas want to do? It wants to move up towards lower pressure, right? It's under some pressure. It wants to move up and out of that pressure. Just like the bubbles in your bath, right? You scramble the water around in your bath or in your sink, and you're going to make bubbles under the water, but then those bubbles, what? Rise up to the surface. Same thing is true when you open soda, right? What happens to the bubbles? Shh, out they come, trying to get to lower pressure. You make bubbles in your lava flow. Those bubbles are going to try and rise to the top of the lava flow. But where is your lava flow cooling down the fastest? The top. So if we have here the bottom of the flow, and here's the top of the flow, notice how there are very few bubbles down here at the bottom, but a lot of these vesicular holes indicating gas bubbles near the top. Why? Because down here, while it was still hot and not as sticky, not as viscous, all those bubbles percolated their way up there where they encountered that highly viscous cooling lava and got stopped and trapped and made those holes we call vesicles. You'll usually find a lot near the top of the flow, and very few near the bottom. Okay. We go to aphanitic? All right. Phaneritic. Phaneritic igneous rocks have large crystal sizes, easy to see. Now they can't be too big. If they're too big, let's say larger than 2 centimeters, most of them larger than 2 centimeters, okay? Then we enter a whole new category that I'll talk about here in a minute. But phaneritic, easy to see, so larger than microscopic, but below that kind of 2 centimeter cutoff, okay? This is like that granite I passed around earlier. Easy to see those minerals, right? However, not all phaneritic rocks are felsic, like that example, okay? You can have mafic phaneritic rocks. That one here called gabbro that I'll pass around in a minute. Large crystal sizes. Mafic or felsic, just by looking at it. Is it more dark crystals or more light crystals? We're dark crystals, which means it is what composition? Mafic. But it's also phaneritic because there are large, easy to see crystals in there. Okay? So composition and texture are independent of each other, but we use both of them to describe. Okay? So, phaneritic. This is granite. That is a phaneritic felsic rock. This is gabbro. That is a phaneritic mafic rock. This is diorite. That's a phaneritic intermediate rock. So on and so forth. Large, easy to see crystals. Then we have porphyritic. And this is what happens when you have both aphanitic and phaneritic. You have a substantial number of microscopic crystals, but you can definitely see some larger crystals. and they're usually different colors. Okay, so you might have a darker background of microscopic crystals and interspersed with lighter, large crystals that you can see. Case in point, this guy right here. Porphyritic, both aphanitic and phaneritic sized mineral crystals present. What could cause this, do you think? What do you think?
Change of environment,
Be specific.
like maybe that if it was growing somewhere and something happened to move that mineral somewhere else, and that's where it made elements.
I like where you're going with this. You said if something happened to melt those minerals and then something else happened and made the rock that way. Yes, but let's get more specific than that. You remember we talked about melting temperatures?
Difference in air, I was gonna say difference in air temperature. or
Not
pressure.
necessarily air temperature. This is probably happening, at least to some extent, underground, because we have larger crystals present, right? Air temperature may not have much to do with this.
Pressure.
Not necessarily pressure either. This has to do with our conversation about partial melting that we had earlier. Let's say I have a rock like, diorite. And I heat that diorite up and melt some of it, but not all of it. I still have a few crystals that have not melted yet. And then, instead of letting it cool off slowly, I all of a sudden expose it to less temperature near the surface. Let's say that it gets pushed up near the surface. It melted fairly deep down, but then got pushed up to the surface or near the surface. What happens to my melted rock, my lava, or magma if it's near the surface still, right? It's going to cool how quickly?
Pretty quick.
Quickly. And make what size?
Small.
Small. That's our aphanitic. That's the tiny little microscopic darker background that you see there. And the other crystals, those are what are left from the original rock that didn't melt in the first place.
That's exactly what I was
Yeah, isn't that interesting? And the opposite is also true, by the way. Okay, you can have things. You can have a total melt that cools off, where that starts to cool off, and you make those larger crystals. Instead of being left over from another rock, they form in this magma that's cooling quickly, and then all of a sudden, that magma that was deep underground, like shoved near the surface, and the rest of it cools quickly. Okay, so there are a couple ways this can happen, but when it does happen, you make that texture porphyritic. You cool with that?
Interesting.
Okay, then we've got glassy, and a glassy texture, well, that's obsidian and glassy. It looks like glass, right? So let me show you some obsidian, actually. Look at that.
Wow.
Yeah. What does that look like to you?
Those they put in the
Like tinted glass.
It looks like tinted glass.
Like the ones they have at church.
Yeah, it kind of looks like stained glass, right? It's got that distinct coloration to it. Where does that color come from?
The unmelted mineral. The unmelted minerals in lava.
The minerals that didn't like come together.
Sure, think of them as minerals that never formed. The minerals were never born. The ingredients were there for them, but now they're trapped between all the silicon tetrahedrons that were frozen. Think of this as like frozen lava. Okay? The only thing that formed were the silicon tetrahedrons in that split second before it cooled, and then whoosh, everything else got stuck in there between it. Okay? It's kind of like frozen lava. And it's got that kind of greenish tint to it now because of all the other elements in there that are stuck between the silicon tetrahedrons. Same reason why amethyst is purple. It's quartz. It is quartz. It is SiO2. That's its chemical signature. But there's a little bit of iron stuck in there. from its formation process, and that's what gives it that color. Same thing with obsidian. What else do you see in that obsidian? What do you see in it?
Bubbles.
Bubbles! You'll see as this goes by, it's full of bubbles. The gases that were forming as it started to cool down and then got trapped and they got quenched. Okay? You can pass around this direction this time. This is some black and red obsidian. Okay? We call that mahogany obsidian. But there's lots of different ways that you can form obsidian. There are some really interesting ways too. In Hawaii, because the volcanoes are right there next to the ocean, oftentimes when Hawaiian volcanoes kind of spit out lava, they'll spit out these kind of like long stringlets of lava, which will fall in the ocean.
The French Forbidden Cups? Or are they like that?
Pele's tears, is that what you're talking about? Like the teardrop shaped one?
Yeah.
I call those Pele's tears. The natives in Hawaii call those Pele's tears.
Oh, okay.
Okay, but yeah, that's essentially it. Except these particular ones I'm talking about make very long, thin ribbons that then fall in the ocean and instantly quench and make that blast. But they don't make glass like that. They make long strands of glass that then wash up onto the side of the ocean, on the side of the beach, like this. They call that Pele's hair. Pele is the Hawaiian goddess of fire, by the way. So the ones that, the drops of lava that fall into the ocean, as they're going through the air, they make this sort of natural aerodynamic shape of a teardrop, much like rain does. And then they hit the ocean and instantly quench. They call those Pele's tears. And then these long stringlets that make these bunches of very thin kind of wires of obsidian glass, those are called Pele's hair. But they are obsidian. Then we've got pyroclastic textures. A pyroclastic texture is one that is formed from the process of a volcanic eruption. Now, pyroclastic rocks themselves do not form from the process of cooling lava or magma, but they are still considered igneous rocks because they are the byproduct of a volcanic eruption, which is in the igneous process. Okay? So these will form when ash and other debris that gets blasted off of your volcanic eruption gets compacted and forms a rock. Okay? Like this. This is called volcanic breccia. This is a bunch of ash and volcanic debris that got welded together because of how hot that ash was when it landed on the ground. Okay? Now you're going to learn about a kind of rock called sedimentary rocks next week that look very similar to this, but are not formed through volcanic processes. It may be easy to confuse them, not in my class necessarily, because I only give you pyroclastic rocks to identify during this week. Next week, when you get sedimentary rocks, you won't get any pyroclastic rocks. So it should be easy to not confuse them in my class, but out there in the wild, sometimes it can be hard. And then finally, we've got pegmatitic rocks. Now, a pegmatite is very cool. Ha. That was a joke, I didn't even mean to make it. You'll understand it in a second, okay? When a magma chamber, which is a body of magma under the ground, okay? Can you make sure that gets faster? When a magma chamber underground cools off, it's at the end of its life cycle, you're going to be left with a whole bunch of random stuff at the very end in that magma chamber that did not easily bond with anything else, usually full of a whole bunch of rare elements. Pegmatites are extremely valuable to mine because all of the rare elements that don't easily bond with other stuff have been left over to this point. So you will usually get extremely large crystals, and that's where that large grain size comes in. Remember I gave you that 2 centimeter cutoff for faneritic? Anything larger than that, let's call it a pegmatite, okay? This is a feldspar crystal from a pegmatite. One single crystal, and it was bigger than this, okay? This is just, it's broken, okay? That is our feldspar crystal. The largest feldspar crystal, I believe, on record ever found was the size of a 2-story house. Yeah. And this is a pegmatite in Mexico, in the Nika mine. for reference, that is a man. Right there, that's his, that's a left, right there. My uncle's actually been in this cave. I have a picture of my great uncle in that cave. He was a geologist, kind of an inspiration to me to become one. But I would already have a picture of myself in that mine if I could, but they closed it to the public to protect it because people started trying to take out chunks of crystals. You have a question?
They're just like, so they're like minerals that were left over.
They are rich in rare elements because they are left over because they were not incorporated into all the things that came before. However long it took, 100 million years for this magma chamber to cool off, and while it's doing that, it's making all sorts of different minerals. What's left over in a pegmatite is all the stuff that did not easily bond before, but has no choice but to now, because the rest of the magma chamber is gone, and it's reached a point of such low temperature that it has to bond with something. And so you get these extremely large, well-formed crystals, usually rich in these rare elements. Okay? And that's why my joke earlier about how pegmatites are cool, now you understand why that was funny. And I didn't even mean to make that joke, so. Okay. Any questions about pegmatites? No? All right. Now, let's talk about how we name igneous rocks, how we tell them apart from each other, all right? We do so based on what you have learned about today. That is, namely, their composition, their texture. Okay, those are the two big things. I'll ask you a few more things on the lab. Tell me if you think this is mostly light silicates or dark silicates. Tell me the general percentage of dark silicates that you see in this rock. If it looks like 100%, you tell me 100%. If it looks like 50%, then it looks like 50%. And that's what you put. Okay? Those are the big ways that we identify them apart. Okay? Just a very basic example. If I have a phaneritic rock that appears to have a felsic composition, it's going to be granite. Right? There may be some more subtlety to it, some more nuance, but I'm not going to teach you that in my class. This is an introductory class. I'm not turning you into geologists. I'm simply trying to inspire you to become one. Right? So, if it is an aphanitic rock that is mafic in composition, it's a basalt. It's that easy, at least within the bounds of this class, right? There's a few more things we'll talk about on the lab, but that's mostly. So let's talk about some of the more common igneous rocks, starting off with granite. And the first thing I'm going to tell you about granite, how many of you, I think you're the only non-high school student here, aren't you? You're in high school? Or you're not? Okay, so I have two non-high school students out of all of you here. I'm assuming neither of you own a home, though. Have an apartment? Okay. At some point, all of you, fingers crossed, are going to become homeowners, and you're going to have to choose your countertops. And when you do, I guarantee whoever is trying to sell you a countertop is going to lie to you. I have yet to meet a countertop salesman that didn't. I have a house built by the Beaton Bow folks just north of town here. Okay, I built it about 2.5 years ago. Love my house. But when I went to go pick my countertop options, I had them build my house. When I went to go pick my countertop options, they had a whole bunch of stuff waiting for me, and it said granite, this type of granite, that type of granite, that type of granite. And I went through it and I went, not granite, not granite, not granite, not granite, not granite. And the salesman's going, because I caught him in his bluff, right? They will try and sell you granite stuff. It's not really granite. If I have one goal in my class, it's that all of you will be able to leave knowing exactly what is granite and how not to get ripped off by a countertop salesman. Okay. By the way, the same thing is true for a gravestone salesman. Okay, they'll do the same thing. They'll try and market you a rock that is not the kind of rock that it should be. Okay, so now you will know. So how about that? You're learning life skills in my class too. How interesting is that? How valuable is my class? Okay, so granite is a phaneritic, felsic, igneous rock with a high quantity of silica, mostly in the form of quartz. Granite is high in quartz. This chunk of granite countertop I just found surrounds you, there's a lot of that gray quartz in there. Granite is valued for how hard it is, how great of a building material it is, mostly because of that quartz. Let's think about the minerals in this granite. We've got some biotite micas in there. That's pretty soft. Okay, about 2.5, 2 to 2.5 on that Mohs scale of hardness. You don't want to build something out of that. We've got this pinkish, salmon pink, whitish feldspar. That's 6 to 6.5%, or 6 to 6.5 on the Mohs scale of hardness. That's about as hard as steel. Okay, steel is slightly softer than that, around 5.5 to 6. Okay, then we've got our gray quartz. Anyone remember where quartz is on the Mohs scale of hardness?
Above crystal,
The Mohs scale goes 1 through 10. Remember? Where's quartz on that?
7.
7! Bingo! Well done. Okay. Harder than steel. Harder than anything else in there. These tightly bound, interwoven minerals would be a lot softer. This substance, this rock would be not as valuable to build with if there weren't so much quartz in it, lending it that hardness. Okay? Very good for something like a countertop. Definitely get granite. If you can't see quartz in it, you're not looking at a good granite for a countertop. And it may not be a granite at all. Okay? They'll try and sell you marble as granite sometimes. And spoilers for the future, marble is about a 3, maybe 3.5 on the Mohs scale of hardness. So you don't want to do that. That's like drop a butter knife on it wrong and you scratch your countertop that. Okay?
Boo.
Boo. Okay. Rhyolite. Rhyolite is the aphanitic version of granite. They are both felsic. These two have probably the same composition when you look at them, or nearly the same composition when you look at them chemically. If I were to break them down and run them through an X-ray diffractor machine or an X-ray fluorescence machine, however I wanted to figure out exactly what elements are in these, they would have nearly the same composition. But why do they look so different?
This one cool down fast.
This one cooled down faster and has smaller grain size. Exactly. Okay, here I already passed around the granite, but we can't pass it around together, right? They are both felsic. Let me actually just show this to the camera real quick. Okay? This is that rhyolite. Microscopic grain size, which means aphanitic texture, but felsic. Okay? Still has feldspar, still has quartz, still has all of that, but they are microscopic. It's actually pretty rare to find rhyolite flows on the surface. Yellowstone, there's actually a substantial number in Yellowstone because of the unique character of Yellowstone, which, believe me, we will talk about Yellowstone. Okay. Now, obsidian. I already passed around the obsidian, but it wouldn't hurt to bring it up again. Why am I calling this felsic? This may have come from a mafic flow, but why am I calling this obsidian felsic?
Made with silica.
It's pretty much entirely just silica, which makes it a light silicate. It doesn't have inside of its atomic composition, its bonds, okay? It doesn't have the irons and magnesiums. Those are present, giving it the darker color, but it's not actually in the bond itself, okay? So that's obsidian. Then we have pumice. Y'all have heard of pumice before? How many of y'all ever been to a spa or a retreat of some kind, like a self-care retreat, and they give you a pumice stone to like exfoliate your skin, use on your feet? Yeah? Feels kind of good. It's nice. It takes off the outer layer of dead skin, some calluses. Did you know that was a rock? Did you know that was an igneous rock? Did you know that was formed from a volcanic eruption? Yeah. This is pumice. This is essentially obsidian with so many gas bubbles in it that it kind of forms this almost sponge-like looking texture. Those are all gas bubbles. Think of this as the root, the foam that comes out of your root beer, or whatever your preferred carbonated beverage is. Imagine you shake that thing and then you pop that sucker open. What comes out first? There are bubbles, okay? But around those bubbles, that fluid it's around the bubble that makes the bubble in the first place. That's some of the stuff from down below, right? So you've got some of that stuff from down below, which has cooled off so quickly that it's made glass. But inside of that glass are so many bubbles that it makes this sort of texture that we value so much for exfoliation. That's pumice stone. There are so many bubbles in this that it will actually float on water. Okay? Pumice floats on water.
Is that what they use for that rock subscription?
Yeah, that's pumice stone. That's for exfoliation. Anytime you go to a resort or spa, they usually have some of that. You buy sticks of that stuff at Walmart. Okay. How are we doing? Am I losing you? No? You doing all right? Okay. Andesite. Andesite is the intermediate aphanitic rock. Andesite. Why is it called andesite? Well, there happens to be a mountain range in South America called the Andes. Y'all familiar with this mountain range? This rock was characterized over there. And we name it andesite because there's a high quantity of it there. Okay? It's where it was extensively studied, and so the name kind of went both ways there. Okay? So this is an intermediate, which means that it's somewhere approaching proportional values of light and dark silicates. Okay? It's in that range of proportionality. Okay? And nearly microscopic minerals. Most of these are microscopic. There's actually a few in this particular sample you can see with the naked eye, but the vast majority of them are in fact microscopic. So this is an aphanitic igneous rock. Aphanitic intermediate igneous rock. Andesite. There's that phrase again. Normal rock. Okay. Is he doing okay over there? All right, diorite, which I actually already passed around, but I'll do that again. Diorite is the phaneritic version of andesite. You can easily see all of these, right? Some people will call this salt and pepper rock for obvious reasons, right? Some people will call this zebra rock, though it doesn't have any stripes, okay? It's just got those colors, okay? It appears to have approximately equal proportions of light and dark silicates. Obviously intermediate, you can easily see them, therefore diorite. This is one of the rocks people most commonly attempt to sell as granite. Diorite may contain at some times some quartz. Most diorite doesn't have quartz, at least not quartz that you can tell is there. Some diorites do have them, most don't in high quantities, and the amount of dark silicates in there doesn't make for a great countertop. So without the quartz and with the high quantities of dark silicates, you're not looking at the best product there for what you want. Okay.
Like at the end, it's better to go mine like granite.
You're gonna mine your own granite and make your own countertop?
Yeah.
I mean, you could start a countertop business. There are a few here in town. I usually go dumpster diving behind their businesses. No, they'll throw away good stuff sometimes. Actually, in my storeroom back here, I've got a couple of slabs of rocks I found back there. Because every now and then they'll be cutting a countertop and they'll mess up and like, God, I can't really use that anymore. And then they'll just chuck it out because they can't use that slab. So then that's when I go, whoop, and I go in there and I pull it out. And I don't know, maybe I'll do something with them sometime. What I would really like to do is have a hallway display where I can have like cuttings of different types of granite, and I can describe, like have a little informational plaque underneath it saying, this is this type of granite from this place in the world. This is this type of granite from this place in the world. I'd love to be able to do something like that. And maybe after I collect enough of them and get a rock saw that actually works. The one that I have over here is from like the 80s. I'm free to even turn it on. So, all right. Now let's talk about mafic. Mafic, aphanitic igneous rock. We already talked about that. That's basalt. Basalt is the most common igneous rock on the ocean crust. Why do you suppose that is?
Most common what on the what?
Most common igneous rock on the ocean crust.
Because it cooled down really fast.
It cooled down really fast. That explains why it is aphanitic. Can anyone tell me why basalt itself is the most common? First of all, it's the most common extrusive igneous rock on Earth. Why? Well, because it forms mostly at the bottom of the ocean, and most of the Earth's surface is ocean, right? But can anybody tell me why it is so common underwater on the ocean crust?
Underground volcano.
Exothermic vents.
It's coming from volcanic vents and volcanoes, yeah. All right, that's fine. I actually haven't finished explaining, giving you all the things you need to finish this logic train. I just wanted to hear what your ideas were. Okay? It's totally fine that you can't tell me the answer to that now. You will be able to tell me here pretty soon now. Okay? Maybe not today, but by the end of the week. Okay, I already passed around that basalt. Oh, it's right. It's here back on the tray. This is that basalt. Okay, I passed it around a few times. Camera. Come on, buddy. Stay with me here. All right. Now, the phaneritic version of basalt is called gabbro. Same composition, mafic, but now it is phaneritic. Large crystals, easy to see, mostly dark silicates.
Large crystals.
So your ocean crust has that top layer of basalt. Underneath that basalt is the gabbro. Again, we'll dive more into that later.
Does that have to do with the cooling process? That's why they're always underneath the.
Yes, the deeper you are, the closer you are to the mantle, the slower things cool down, and therefore that's where most of your phaneritic rocks will form.
But basalt specifically. But basalt specifically.
Basalt will form nearer the surface, which is why it's aphanitic.
But that you said is mostly underneath the ocean floor.
No, it's the ocean crust.
Oh.
When I say surface, imagine I'm talking about the atmosphere and the ocean in the same context. The ocean, the Earth's crust is the ocean bottom as well. Okay, regardless of however much ocean is on top.
So it's all one. Just kind of like, yeah, had the option to throw out
Think
all
of
the water.
crust. Yeah, think of the crust itself as the skin of the planet, where sometimes it's thinner and sometimes it's thicker. Like the skin on your feet, like on the bottom of your foot, is thicker than the skin on, say, your pinky finger. Okay, just as an example. Okay, like around the knuckle right there, it's fairly thin, right? But on the bottom of your foot, it's nice and thick and well-developed pad for walking on. Think of the thicker part of our crust as the continent, and the thinner part of our crust as the ocean crust. Okay? No matter how much ocean is on top of it. All right. Then pyroclastic rocks. We've got something called welded tuff. This is essentially ash that has all been welded together because it was extremely hot when it landed. The ash blew out of the volcano, extremely hot, shards of microscopic glass. It landed on the ground and it piled on top of itself, and this superheated microscopic glass kind of compacted and welded together and made this tough rock, which we actually call tuff. T-U-F-F.
Tough.
Okay? Yes, T-U-F-F. Make all the jokes you want. There are some funny rock names out there. Wait till we get to the rock called wacky. Yes, it is actually wacky. It's called wacky. Yes. Some people call it whack. My teachers all taught me that it was wacky, so I've kept it as wacky. And then we got volcanic breccia, which I already passed around earlier. Very similar to our tuff, however, it also incorporates larger fragments that were blasted off the volcano. It's not just ash, it's also just the debris and the shattered pieces of rock from that eruption. Okay. All right. Let's talk about where magma comes from. Now, we already discussed the fact that most of the Earth is solid. So many people are taught in school that once you get below the crust, It's just liquid. This is not correct. Okay, it is solid down there too. It just, like I said before, is squishy. It's hot enough to be melted, but it cannot be melted. The deeper you get underground, the hotter it gets. We're all familiar with that concept, right? You need a simple explanation for that, or a simple example. This is the Tautona mine in South Africa. This is the deepest mine in the world. Here's a cross section of it. This cross section is actually outdated. I believe this is from about 2015. Okay. At that point, the mine is 3.6 kilometers deep. It's deeper than that now. It is so hot down there that the men who go down there to work can only do it in extremely short shifts, and then they have to go and get refrigerated for a while so they don't die of heat stroke. This is one of the places in the world that they are spending the most money on experimenting with robotic workers. Okay? Robot machinery, robot mining carts, robot, however much, as much robot machinery as possible to keep this mine active and not put people's lives at risk because of heat stroke. Okay?
What are they mining?
What are they mining? A couple of different things. I think they've got some calcium-based minerals that come out of there. I'm not actually, they might actually have some gold. I don't remember exactly what this particular mine produces. Some of the largest gold mine companies in the world are out of South Africa. But I'm not familiar with what this mine in particular mines. That's a good question. I'm gonna look that up after we're done here. I'll give you an answer. Okay, like I said, I won't lie to you if I don't know something. Okay, now, the hotter it gets, or the deeper you go underground, the hotter it gets. This is something called the geothermal gradient. The geothermal gradient. It's a good thing to write down. Okay? Now, what is the geothermal gradient? The geothermal gradient is the rate at which heat increases the deeper you go underground. It is not a linear path, believe it or not. This hockey stick here, that's our geothermal gradient, this red hockey stick. Here on this graph, we've got three types of data, okay? Or three axes of data. We have depth from 0 to 500 kilometers. We have temperature from 0 to 2,500 degrees Celsius. And here on the same axis as our depth is pressure, because pressure increases fairly consistently along with depth. Okay, so from 0 to 150 kilobars in temperature. Now, what do we see here? This is our geothermal gradient. This pink line is the partial melting point for the rock peridotite, which is this green and black one I showed you makes most of our mantle. So we're talking about the melting point of mantle rock, right? So this is where it starts to melt, and this dotted line is where it is completely melted. Notice how our geothermal gradient and the partial melting point for peridotite don't actually meet. They come so close. They're almost kissing right there, but they're not perfect. And that's why our mantle is still solid. It can't quite cross that line. What has to happen? Something has to happen for us to get magma from this situation. There are three things that could happen here. The first one is an increase in temperature. What happens if I increase the temperature? Okay? This is my axis for temperature. If I take my geothermal gradient and I push it to the right, what happens? I'm increasing temperature. What happens?
Starts melting.
We have passed the melting point. Boom, bada boom. We can have melted mantle rock. Magma forms in the mantle in that particular location where this happened. How can we increase the temperature beyond the ambient temperature of the mantle? Tectonics. Not necessarily pressure. We'll talk about pressure in a minute, okay? It's going to be tectonics is probably the most common example. When you have two plates that run into each other, one is scraping under the other one. Out comes the pens, okay? If I have, let's say, a nice thick continental plate and a thinner oceanic plate right there, can you imagine how much friction there is right there along this zone? Do you think that friction is going to increase the temperature as these two titanic octillion-ton masses of rock are scraping past each other? I don't know if it's an octillion, I just needed a big number, okay? That friction is going to be huge, and it's going to increase the temperature. And as you increase the temperature, whoop, partial melting, you get magma right there. That's one way. What's another way? What did you say earlier? Pressure. But what are we doing to the pressure? If we want our geothermal gradient and our melting point to intersect each other, what do we need to do to the pressure? Huh? Compress it. So you're saying increase the pressure? What happens if we increase the pressure? Let's take this point and increase the pressure. And increase the pressure. It's gonna keep going and going and going, and it may get close, but it's not gonna do it. Okay? Instead, what do? If we decrease the pressure, let's say we're at this point, okay? We decrease the pressure. So our pressure decreases moving up, our geothermal gradient, we're decreasing the pressure. Eventually, once you decrease it enough, they have passed each other. So by decreasing the pressure, we are allowing our mantle to now melt because it is at the right temperature already for that pressure. How can we decrease the pressure? Let's say we have two plates diverging from each other. Here we have a divergent plate boundary, okay? They're moving opposite directions away from each other, right? Right here between them, where they both rise up, there's this open space where mantle rock can press up to where the plates are thinner. Right here, the plates are very thin where they're pressing away from each other, where they're separating away from each other. And in that zone, we're going to have far less pressure than we do in the rest of the mantle. And because there's less pressure, that mantle rock is going to be able to melt, and you get a pocket of magma there at the divergent plate boundary, which is what is making the magma being added to both sides of this divergent plate boundary. That's how we make new tectonic plate mass. That's the second way that we can get melted rock in the mantle. And the third way, just add water. You guys ever seen those kits? Sometimes it's like a baking kit. It's like, instant muffins, just add water. You know? You probably are. Look at that and go. Beginners, right? Or sometimes it's really funny. Like I saw a pool, like a kiddie pool. It said instant kiddie pool, just add water. That was funny. That's good. But it's true here too. What do I mean by this? Well, okay. This is going to be a little bit hard to swallow, perhaps, but I need you to open your mind and think of this from a chemistry point of view. When I throw water on a fire, what happens to it?
Gas.
It puts out the fire. Okay? Why does it put out fire? You're cutting it off from its fuel source. You're damping its temperature. You're absorbing its temperature. You're doing a lot of things to it. And so typically when I talk about fire and heat, or anyone talks about fire and heat, you're naturally going to think water is the antithesis to heat and all of that. Really all it's doing is absorbing that heat, right? So listen to this. Water lowers the melting point of rock. And now you all think I've gone nuts. I'm not talking about the physical capabilities of water. Sure, water can absorb heat. Sure, water can cut fire off from its oxygen source. All of that. But I'm talking chemically. Chemically speaking, you add water to a rock and you have lowered its melting point. It will now melt easier. I'm not going to go into the chemistry of why. That would take the rest of the day. We're not going to do that. Okay? Instead, I need you to trust that this is the case. And I'm going to tell you now, it's more complicated than I'm saying. But all you need to know is that you put water into the equation and your melting point drops. What happens if our melting point drops? Okay? What happens if I take this purple line and now it takes less heat to melt it? What direction does it move?
Left.
To the left. Take it back now, y'all. Right now. 2 hours this time?
Yeah.
Okay. So we've now moved it that way, and now they have crossed, and we have melted rock. That's the third way. Now, how can we introduce water to the mantle to make that happen? Any ideas, anyone?
In the ocean.
From the ocean? How does water from the ocean get that deep?
Water pockets.
Water bottles?
No, water pockets.
Water pockets? Pockets of water? All right, my blue pen is gone, so I'm gonna use purple.
How does water get that deep in the what?
Yeah, how does water get under the crust to the mantle where it needs to go for this to happen?
Geothermal vents.
What?
That's the geothermal vents.
Geothermal vents, stuff's coming out, not going in.
We dig a hole.
We dig a hole. The deepest hole we have ever dug was about 17 kilometers and it didn't make it to the mantle. There is actually this really cool project to dig below the Earth's crust to the mantle or very close to it to power a geothermal energy production facility. They're working on that right now. The deepest hole that's ever been attempted, but even that is not gonna, you won't be able to introduce water to the mantle and melt it.
The earth absorbs the water?
Huh?
The earth absorbs the water?
What part of the earth absorbs water?
There's crust.
What part of the crust? You're getting there.
I don't know.
Anyone want to help them out? What part of the Earth's crust would most likely absorb water?
Tectonic plates.
What tectonic plate?
Or the ocean.
The ocean plates. Why would the ocean plates absorb water?
If they have water on them.
They're underwater. So there's going to be a lot of water that's been absorbed in these top layers of rock. And what happens when that ocean plate gets subducted under a continental plate or another ocean plate?
The water will sink.
The water is going to go down with it. And the deeper it goes, the hotter it gets. And what happens to water when it gets hot? It gets superheated and it rises. So we have a whole bunch of water from these plates trying to get back up through the surface. And what do they need to go through to reach the surface? The mantle. And as that rock is introduced to the mantle, what happens to our melting point?
It decreases.
It decreases. Boom, bada, boom. You get pockets of magma. Right there.
Neat.
And that is why we have so many volcanic mountain ranges on coastlines. These volcanoes pop up where these pockets of magma form from this process come up and reach the surface. That's your Andes, that's your Cascades, the Rockies to an extent.
That's why there's basalt and.
Now, well, we'll talk about what kind of rock that is here in a little bit. But for now, that's the third way. Any questions about how you make magma?
That's pretty cool.
Now, I know that y'all are struggling, so we're gonna do our M&M activity here, okay? Just to kind of wake you up. If you need to stand and stretch for a second, go for it. I'm just gonna keep talking so you can make the most use of our time. Okay, I wanna give you all at least an hour to work on lab stuff today. So I'm gonna try and bust through this, okay? So, this takes us to Bowen's reaction series. Bowen's reaction series is by a guy named N.L. Bowen, okay? But basically, what this guy did was he conducted some experiments in a lab, and he figured out that at certain temperatures, certain minerals will form and melt. Now, how does this work? What does this matter compared to magma? Remember our conversation about partial melting? Because not all minerals have the same melting point. A melting point is also the crystallization point. If a mineral will melt at 1100 degrees Celsius, then when I take my magma, which is hotter than that, and decrease it at 1100 degrees Celsius, that mineral will start to form. You understand that? Perfect. So as a magma chamber is decreasing in temperature over time, you're going to start to form different kinds of minerals. At its hottest, you're going to form our first mineral, olivine. Forms at about 1200 degrees Celsius. Then you're going to form your pyroxenes and your plagioclase feldspars, calcium rich to begin with. Now, as time goes on, and more elements are pulled out of your magma to make these minerals, what's going to happen to your magma?
Become bigger.
What was the misuse?
As time goes on, and you are pulling, let's say, iron and magnesium to make your olivine and pyroxene, you're pulling that out of your magma to make those minerals, what happens to the composition of your magma?
It's melting. Like darker.
Let's say it starts mafic, and you're pulling out the irons and magnesiums. What does it become?
Iron and magnesium.
Light.
It gets lighter, meaning that it is now what composition?
Silicate.
It's gonna require a higher quantity of the lighter stuff, right?
But it's still like a derivative from mafic, so would it be an intermediate?
It's now moved into an intermediate. And as time goes on and you're making more of those intermediate minerals, what's it gonna become?
Felsic.
Felsic, okay. This is Bowen's reaction series. The mantle is ultramafic. Therefore, the magma that we form from one of those three processes we just discussed is going to be ultramafic. We start with ultramafic. We start to form our olivines and pyroxenes. They suck a lot of irons and magnesiums out of the magma to make those minerals. As we remove irons and magnesiums from the magma, our magma itself is going to become mafic instead of ultramafic. Then you pull even more out to make other dark silicates, your amphiboles, your biotites. Okay? And as time goes on, it goes from mafic composition to intermediate. And the same thing keeps going until you reach felsic. So, all that time that we thought, okay, well, there's a felsic magma chamber, well, there's a mafic magma chamber, well, there's an ultramafic magma chamber. All that time, now we know, because of this sequence, Bowen's reaction series, we know, they all start as ultramafic, and they all end as felsic. They go through Bowen's reaction series, making different sequences of minerals as time goes on. That's Bowen's reaction series. And now we will do our experiment with the M&Ms,
Wow.
just to prove this point. Okay, I'm going to pass these out here.
That's pretty freaking sick.
What I am handing out is the same thing that you all can see on the PowerPoint. Okay, it looks like this. This is a magma chamber, homegrown, made it myself. I will take compliments. Okay, you'll notice that on one side there is a temperature scale. That's going to tell you, generally speaking, when these minerals are going to form, or at what temperature these minerals are going to form. Okay, your M&Ms in your bowl each represent elements. Okay, and those elements are going to be bonded together to make minerals. The key for that is down there on the bottom of your page. There you go. Everyone got one, yes? Okay. Now, magmatic differentiation is the process by which your magma starts to change over time as your minerals are forming and pulling elements out of the magma. So let's start off with making the first minerals that form as our magma is hottest. Olivine. Your olivine. Sometimes it can be difficult to tell the colors up there, but that should be 2 purples and an orange. Yes, 2 purples and an orange. By the way, for the purposes of this exercise, I did not give you anything to represent oxygen. Remember that along with those silicons, there's always going to be between 4 to 2 oxygens. I just didn't have a color of M&M that I had enough of to represent the quantity of oxygens that you would need for this experiment. So the oxygens are implied. Okay?
But they are there.
They are there, just not in M&M form.
It's in the air.
Okay, just a quick recap. We're doing the M&M activity. You have a sheet at your place that is a magma chamber, and we are using M&Ms, which each represents an element, to make different minerals. And you're going to see how over time, the ratio in your magma chamber, which right now should be pretty mafic, is going to change over time. Okay, so we have formed our olivines. 2 purples, 1 yellow, or 1 orange. Yeah, 1 orange. Everyone there?
Yes.
Good. That's going to go down there into our ultramafic section, down near the bottom. Those form when our magma chamber is still ultramafic. Then we're going to form our pyroxenes. That is a green and 2 oranges. And that's going to go down there and join olivine, but it's kind of got to ride that line between ultramafic and mafic. Okay? Then we're going to form amphibole.
Whoa.
Yeah, whoa. Okay, so that's 1, 2, 3, 4, 5 greens, and 1, 2, 3, 4, 5, 6, 7, 8 oranges, and 2 yellows. That's our iron, our calcium, and our silicon.
Wow.
Did you lose an element?
Maybe one.
That is going to go down and join them in the mafic section. Because we get amphiboles in mafic and in intermediate, so it's going to kind of ride that line. Then we get a little bit more of a simple one. Calcium feldspar, 2 blues, a yellow, and 2 oranges. That's aluminum, calcium, and silica. That's going to move on down here, ride that line, because those will often appear as smaller quantities in mafic rocks and substantial quantities. Why is that camera over there? I'm sorry for those of you watching this later. You can see where we're at. We've got our olivine, our pyroxene, our amphibole, and our calcium feldspar, which is the principal ingredients in intermediate rocks. Ready?
Yep.
What's happening to our chamber? It's slowly emptying, right? We're losing a lot of our elements. We've lost most of our magnesiums and irons now. We have now fully moved on into intermediate phase, probably merging on felsic, which means that the next things that form, potassium feldspars. Okay, that's a red, a blue, and 3 oranges. That's going to ride this line here between intermediate and felsic. And we've got one more dark silicate that's going to form, our biotites. So this is going to take up a lot of the irons or magnesiums we've got left. So 3 purples, 3 oranges, a blue, and a red.
Biotite.
I used to do this with mixed candy, including, like, it would have some Skittles, and it would have, you know, little fruity snacks, and it would have jelly beans. And at the end of every experiment or every exercise, we did this. Inevitably, I would have just bowls at the end full of black licorice jelly beans because no one wanted them. And then I would just have all the black licorice jelly beans myself because I actually have taste and I like them. Okay. Instead, M&M's seem much more neutral for everyone. Okay, so then after biotite, which is down here riding that line as well, we've got muscovite. That's going to be 6 oranges, 2 blues, and 2 reds. The light silicate muscovite.
I don't really ever realized how much silicon is in the earth.
Yes, there's a lot of silica. Remember, you're only making one bond right here. You're making one unit, I guess you could say, of each mineral. And then finally, or maybe not finally, but here at the end, we finally form quartz, 1 orange. It's SiO2. So there are 2 oxygens implied on that 1 orange for quartz. One of the last things that forms, quartz. That's why it's only in felsic rocks. Now, what has that left us with? What do you have left in your chamber?
2 blues.
2 blues?
2 blues, 2 browns.
2 blues, 2 browns,
4 oranges, 1 purple.
4 oranges, a purple,
1 yellow.
Red.
a yellow. What would you say that the ratio of dark to light is? Hardly anything left that could form a dark silicate, right?
Yeah.
You're not going to form really any dark silicates left. That ship has sailed. Those formed already. You left a lot of leftovers, including a high quantity of what are browns?
Rare
Other.
materials.
Huh?
Rare materials.
Rare materials. Where before, there were only 2 in there in the vast quantity of everything else. They haven't been used for anything. They don't bond easily with anything. And so now here at the very end, they have a much higher ratio. They have no choice but to bond here at the end of the magma chamber's life. And that gives us the rare elements that we see in our magma chamber pegmatites. This is Bowen's reaction series. How the sequence in which a magma chamber will change over time as it cools down. Okay? How do you all feel about that? Does that make sense? Good. You may now eat your M&Ms. I set you free. Okay, let's breeze through the rest of this so you can have some lab time. Now, as your magma chamber is cooling off, it's going to go from this nice hot body there. It's going to move on down. You're going to start to cool off. You're going to start accruing minerals along the edges as Bowen's reaction series goes on, starting with olivines and then pyroxenes and then yada yada. And here near the end, you're going to have a very felsic composition. Your magma at the top is going to have become felsic, or it's going to get pushed out as felsic. Lavas and all of that. However, there are a few things that can happen to shake that party back up. Okay. First of all, what happens if you've partially gone through Bowen's reaction series? Let's say we're in an intermediate phase, and then all of a sudden, a fresh new magma body rises up and incorporates itself into you, right? And both these bodies join. So we've got an intermediate body, we've got an ultramafic body. They will mix this magma mixing here, and you're going to end up with probably something that's somewhere between mafic and intermediate composition as they are mixing and diluting each other. So that can reset Bowen's reaction series a bit. Set it backwards, if you will. Then, what do you suppose is happening to the rock around your magma body? Is your magma saying, excuse me, I gotta get through here. I'm trying to get up there. You know, I need to get up there. Just pardon me. No, what's it doing? It's melting that rock. And what is it doing to that? Incorporating all the stuff that's melting into itself. And so the composition of your magma body can be changed by the rock that it is incorporating by melting the surrounding rock around it.
Interesting.
Okay. Those are the things that can influence Bowen's reaction series. Yes?
Does the magma ever change color?
Yes. Magmas can change color. As a matter of fact, there's a place out in Africa that I desperately want to go to, where the lava that comes out of the volcano is brown. It looks like mud. it literally just looks like mud. It looks like streams of mud coming out of the ground. But if you touched it, you burn your finger off, you'd catch on fire just like you would any other magma. It's just as hot as every other magma. But it is not the same silica based. It's melted calcium based rock, basically. It's fascinating. I'd love to go there sometime. Okay. So, let's see. Cover that. Hello. Computer, come on. I don't have time for this.
Oh,
Feldspar. That should be your swear word, Mr. Hart.
Huh?
That should be your swear word. Feldspar.
Feldspar? No. What is my go-to? I don't like swearing at all, but every now and then, like something happens. Like, I think I say crap a lot. Yeah, I think I say crap. We freak sometimes. I don't know. All right, now let's talk about partial melting. We already talked about that. That certain things will melt at certain temperatures before other things do. So this is a very simple example. Okay. Here we have three things. We have on the left linseed oil, which has a very low melting point. Let's say that that's our quartz. Then we have ice. Let's say that's our feldspar. Then we have chocolate. Let's say that's our purity. We have, or our amphibole, we have a granite here. You start increasing your temperature, your quartz starts to melt. Why? It was one of the last things to form. It has a low formation point, which means it also has a low melting point. Once you increase the temperature enough, watch what happens when we reach 0. The ice starts to melt. That's our feldspar melting. Okay, temperature is increasing. Let's keep increasing our temperature. The last thing to melt is the first thing to form as the temperature is decreasing from a magma. That's going to be our chocolate. This is how a rock melts. This is how a granite would melt. The first thing to form is the last thing to melt, because that formation temperature is your melting temperature as well. So, as this magma is forming, it's going to push its way up through the rock and it's going to form a variety of shapes. Okay? We call these intrusive bodies or plutons. Okay? So, we differentiate these, we classify these based on their shape and their orientation of host rock. Okay, so it can either be a massive shape, which is kind of a big blob, like you see here, or a tabular shape. So it's kind of making this sort of linear cut along or through the rock. Now, if it's through the layers of rock that were there before, we call it discordant. And if it's along the layers of rock that were there before, it's called concordant. Okay, so let's talk about some examples. The tabular bodies. A dike is a tabular intrusive body that has sliced through the previously existing rock. It is perpendicular to the layers of rock that were there before. So let's say I've got some neatly bedded layers of sedimentary rock, and then all of a sudden the tabular body of them goes shoo, like a pizza slicer went through it. That is a dike. It is perpendicular to those. A sill is the same thing, but instead of slicing through those layers, it was laid horizontally, or not, I shouldn't say horizontally. It was laid parallel to those layers. This is actually a trap that you'll see sometimes. Dikes are not always vertical, and sills are not always horizontal. A dike is perpendicular to the layers of rock there before, and a sill is parallel to them. Okay, just remember that. For our massive bodies, a batholith, which you cannot say without making it sound like you have a list. Batholith. Okay? This is a massive body of magma that is more than 100 kilometers square. It's almost always made out of felsic intermediate rock. Why?
If not that hot,
At the end, when it was just finishing formation, it wasn't that hot. That's Bowen's reaction series. What had it gone through? The whole of Bowen's reaction series. Now it's a body of rock. It's not magma anymore. It's a body of rock, meaning that it went through Bowen's reaction series, and now it is what? Felsiker Intermediate at the end of that series, however long it took. Okay? Okay, so just want to make sure that we're remembering that. A stalk is the same thing but smaller in size. Yeah, sure. And then a laccolith is kind of, you could say, an off branch. Where is it? It's kind of an off branch of one of those. It's where a sill or a dike is kind of broken off from your stalk or your batholith, and then went and filled in something somewhere else, and it kind of picked up the layers of rock above it and kind of forced them upward to make a secondary chamber somewhere nearby. All right, this is the last slide, and we're done. And then you have a lot of time. So, igneous rocks are responsible for a lot of the very valuable resources that we look for today. Okay, in particular around those batholiths, those rare elements that we find in in pegmatites. Those rare elements that we find in pegmatites, excellent mining targets. We look for those a lot. If you ever go to Mount Rushmore in South Dakota, have you ever been there? Yeah, if you ever go, that entire area is mined extensively because it's sitting right on top of a pegmatite. Mount Rushmore is carved from the rock of that magma chamber, and nearby is a very valuable pegmatite mining target. Okay? So there's good stuff everywhere. We can get lithium, cesium, uranium, those 17 rare earth elements that we learned about before. We get those out of pegmatites. They are fantastic. Also, gold, silver, copper. Okay. Oftentimes, what will happen as a magma chamber is cooling off near the surface is the groundwater in that area, as it's kind of making its way slowly through the ground, it's going to heat up because of the proximity around that magma chamber. As it interacts with the last stage of that magma chamber, the pegmatites as they're forming, that groundwater, that superheated groundwater, is going to dissolve a lot of the minerals that are forming, including the precious metals in those minerals. And it's going to carry them far away. This is called a hydrothermal solution. This hydrothermal solution is going to go wherever the groundwater is flowing. And at some point, it's going to cool off enough that that gold and silver and all those other valuable minerals are going to solidify and kind of attach themselves to the rock the water is in at that time. When I worked at the gold mine in Nevada, my job was to take a drilling crew. Me and my drilling crew, we go zzz, zzz, zzz. We just basically drill holes and take sample core, and then we would test those core that came out, and we find, is there any gold here? Basically, we would start where the pegmatite was, or where the original body of rock was, the pool that this rock came from. We mine that out as much as we could, and then we drill holes and track where that hydrothermal solution flowed after the fact. We're talking about like from the Jurassic. We're talking about 100 million year old flow, but we're tracking where it went through the rock by following the gold traces until eventually we find where as much of it was deposited as we can, as much as we can find, and then we put a new mine there called hydrothermal solutions. Okay, and hydrothermal deposits are extremely cool to mine. They're very fun. Very fun to mine. It's almost like you're following clues, right? You're following clues. It's almost like being a detective because you're trying to figure out where the gold went. Okay. Pretty cool.
What does it smell like in one of those?
What does it smell like in what? A gold mine?
Well, no, you said the hydro something.
Oh, hydro. Well, I mean, this is all underground.
Well, yeah.
This is all happening.
So
underground. A hydrothermal vent, like you just go to Yellowstone, they don't smell great. There's usually some sulfur involved. Okay. Any other questions? We're moving to the lab. Okay. You're not getting a new lab today. Lab 2 is going to be assigned on our next lecture. So the rest of today is to work on lab 1.